Hello. Yeah, okay. So my mic is connected now. So yeah, today I'm focusing on Kafka, basically system design. So before the stream, I've already gone through these chapters from Hello Interview. So basically, I'm following Hello Interview and LXU book together for my system design preparation. So I've gone through these I had gone through these before, and today I've revised them. And now right now I'm working going through Kafka because I have mentioned Kafka in my resume, so it's important for me to have a good decent knowledge on Kafka, and I should be able to uh, answer questions around Kafka. That is why. So yeah, that's it. Like I'll go through this stuff deep dive, Kafka deep dive, and also follow this book, and we'll also try to get some questions from ChatGPT and try to solve them and not solve them probably, but read through them so that we can answer questions based on Kafka in a interview, right? That's the like that is the whole point of this preparation. That is right. Okay, so let's continue. Okay, so Kafka, as we all know, Kafka is a distributed event streaming. It is a distributed event streaming platform. Let me do one thing. Let me also mention open for AI. Okay, ठीक है. So Kafka is an open source distributed event streaming platform that can be used either as a message queue or as a stream processing system. So basically, like either we can use it as a queue or as for event sourcing, because in Kafka we maintain an append only log, right? Kafka internally maintains logs for all the messages, so it can be used as event sourcing, for event sourcing as well. And of course, it delivers high performance, scalability, and durability. Let me do one thing. Okay, give me 1 minute. One- Yeah, okay. So after sourcing it now in this deep dive, so okay, the update. So Kafka is mainly used. Uh, basically it can be used in PubSub model as well. So basically for Kafka we have please excuse some components. One is producer. Producer is basically a component which is generating the data, or generating some event, or let's see. So yeah, we have Kafka components. Okay, so Kafka as a producer. So we have a producer which will generate or produce some events. So it's very simple. From naming convention, it is very clear that it will produce some data, some events, some messages, some records, whatever you can call it, anything, records or messages or data or event, whatever. Okay, and then we have a consumer which will consume these records, events, messages, or whatever. Okay, so now what happens is basically the thing is, see, in multiple in distributed systems, the idea is we don't always want synchronous communication. Synchronous is basically, suppose a person A sends a request. So person A is sending a request. Person A sends some request and it reaches to person B, and B will acknowledge that okay, I have received, and then A will see okay, B has received. So this is basically synchronous. That A is sending something and B is receiving and B is acknowledging. So A is waiting until B has received the message or not. So in PubSub model or in asynchronous communication, we don't usually wait for the receiver to acknowledge, or we don't usually wait for the receiver to receive the messages. So the idea is to just push messages, push messages to a server, let's say, and let it be. Like the producer here is least concerned about the consumers receiving the messages. What the producer has done is it has sent the messages. Okay, it has sent the messages, and now consumer may deploy its own strategies to pull the messages. Okay, from this middle box. Okay, so this middle box basically is Kafka. Okay, uh, so Kafka is made up of multiple smaller components. Like basically, uh, let's follow this. So Kafka is made up of brokers. Okay, broker is nothing but a server. Broker is not sorry. Broker is nothing but a Kafka server. Okay, so a particular Kafka cluster may have multiple brokers. So uh, let's just take care of one broker at a point. Okay, so Kafka will have multiple brokers, and broker is nothing just one server. Okay, and these things we can also try. Like I've already tried the coding for it. You can download Kafka and you can just get started with it. So it will be much easier for you to understand. So each broker is responsible for storing the data. So as I said, whatever messages the producer will send, broker will store it, and then the consumer will pull it from the broker. Okay, and obviously the more brokers you have, the more data you can store. Now each broker has a number of partitions. There are some partitions in a broker. Okay, so here we have four brokers. So each broker will have some partitions, and each partition is an ordered immutable sequence of messages that is continually appended to, think of like a log file. Now this ordered is a very important word here, because it is a very common interview question, or maybe a common trick question, something like that, that whether messages inside a partition are ordered or not. So messages inside a partition are ordered. Okay, okay, so yeah, messages inside a partition are ordered. I think yes. Now it's an immutable sequence of messages. Immutable obviously means it cannot be changed. So it will just receive the message, it won't do anything, it will just keep on appending. So it works like a log file only. It just keeps on appending the messages, whatever it receives. Okay. Now, why do we have so many partitions? Because if we have n number of partitions, then we can receive n number of messages. Not n number of messages, but basically it means that we can consume many messages in parallel. Okay. That is right. If we have only one partition, we'll only be able to, you know, uh, get the message in one partition. But like basically, suppose we have whatever, we have some messages. Okay, so they will be present on one partition. But if you have multiple partitions, the messages will be spread across multiple partitions. Now, how will they be present in across the across the partitions, or how will they distribute across the partitions? That depends on the choice of partition key and stuff, and producer can control all that metadata. So we will go into that. Let's see. So each broker has a number of partitions. Partitions are the way Kafka scales as they allow for messages to be consumed in parallel. Okay. Topic is nothing but a logical grouping of partitions. So whenever you configure Kafka, you provide a topic name so that you are aware that what kind of messages you are expecting. Okay, it's a logical grouping. Okay, topics are the way you publish and subscribe to data in Kafka. So basically, whenever we publish data, it is published in a topic. Also, the consumer mentions the topic from which it will receive the data. Okay, and topics are always multiple producers. So obviously, any number of producers can write to a topic. N number of producers can write to a topic. Okay. So difference between a topic and a partition is topic is a logical grouping, while partition is physical grouping. Partition is basically done for, let's say, scalability, and yes, to make Kafka scalable. Okay, and topic is logical grouping. Okay, so a topic can have multiple partitions. Okay, so basically, if you see here, we may have a topic with, let's say, 9 partitions. So a topic can be present across 9 partitions, and these 9 partitions can get scaled across 3 brokers. So in general, we have 3 brokers in a Kafka cluster, let's say. So we have 3 brokers here. Okay, so whatever topic we create, that can be present across all the brokers, and each broker we are saying has 3 partitions. Okay, so we have like 9 partitions in total. Some partition 0, 1, 2 is in one broker, some other partitions are in other brokers, and the topic is present across these brokers. Okay, and partition, so topic can have multiple partitions. Each partition can be on a different broker. Topics are just a way to organize your data. Partitions are a way to scale your data. This is very important. Partition is required for scaling. Okay, and producers are and consumers are uh, nothing different. Producers and consumers. Yeah. So producers are the ones who write data to topics, and consumers are the ones who read data from the topics, which is very basic. Creation is on you. Kafka doesn't care what the data is; it just stores and serves it. Yes. Importantly, you can use Kafka as either a message queue or a stream. Okay. In a message queue, consumers read messages from the queue. Okay, and then acknowledge with the process in a stream from the stream and then process them, but you don't acknowledge. Okay, ठीक है. This I think is maybe an important point, a distinction between a message queue or a stream. Okay, how Kafka works when an event occurs. So yeah, so basically whenever some event occurs, producer will create the message. Now, how to create the message and all that algorithm will be decided by the engineer. Okay, but that message would be sent to the Kafka topic. Okay. Now, there are some important key fields of a message or a record when we talk about a record for a Kafka. Okay, which is the value. So one required field is the value. Otherwise we have 3 optional fields: key, timestamp, and headers. Okay. Now this key is used to determine which partition the message is sent to. This is a very important point. Okay. You might be grilled on this in interviews. The key is used to determine which partition the message is sent to. And timestamp is used to order messages within a partition. Okay, timestamp is used to order messages within a partition. Because now this was important, as I told earlier, messages within a partition are ordered. Okay, so this timestamp is used to order it. Okay, while not strictly required, key is used to determine which partition the message is sent to. If you don't provide a key, Kafka will randomly assign a message to a partition. So when designing, you are likely to be asked about in your interview. You will want to use keys to ensure the order. Choice of that key is important. The choice of this key is actually very important because I have worked on this on a production feature. That is why I'm aware of this. As a quick example, here is how we might put a message on the this. So this is basic Kafka commands. Nothing much. All these are basic Kafka commands. Yes, when a message is published to a Kafka topic, Kafka first determines the appropriate partition. So message is published to a Kafka topic. Now Kafka will determine which partition it should send the message to. Okay. This partition selection is critical because it influences the distribution of data across the cluster. Right. Partition determination. So Kafka uses a partitioning algorithm. Now, if we do not provide a partition key, then Kafka will use its own algorithm to figure out to which partition it should send the message. If the message does not have a key, Kafka can either round robin the message to partitions or follow another partitioning logic. Sorry. But if we provide a key or if we provide some algorithm, Kafka will use that to determine the partition. Okay, this is actually very important because sometimes you would want that a particular set of messages should always go to the same partition. That is it. And because order is preserved at partition level. Okay, across partitions we may not guarantee order. So this is actually very important point. Broker assignment. Now once the partition is determined, Kafka will then identify which broker holds that particular partition. As we saw here, if we have like multiple partitions, some particular broker, if we have like multi-broker, like if we have multiple brokers, some of then which one of these has that particular partition that needs to be determined. Okay, okay. Mapping of partitions is managed by Kafka clustering from a Kafka controller, a role. Yes. So we have a Kafka controller. Now with I think previously this used to be done by a Zookeeper, but in this latest version of Kafka, sorry, uh, 3.3 and more, this Zookeeper thing has gone away, and one of the brokers assumes this role of controller. Okay, okay. So yeah, producer will use this metadata to send the message directly to the broker that hosts the target partition. Now, each partition in Kafka functions essentially as an append-only log file. This is very important. Any partition, it's simply an append-only log file. Nothing much. So whatever messages come, they are sequentially added to the end of the file. They're continuously added. Okay, which is why Kafka is often described as distributed commit log. This is also very important. These are like minor points which interviewer just takes up. If they ask you what is Kafka and you just memorize and say it is a distributed commit log, they might ask why, and what does this mean, distributed commit log. That is why. Okay. Now immutabilities of obviously messages in partition cannot be altered or deleted. Efficiency, disk seek times. Okay. Scalability, can simply add. Okay. Is added a So yeah, every message has an offset. So this offset thing is also required because if some let's say if my API is down for some time and the consumer was unable to consume the messages, so how will it know the last message which it consumed and from where it has to resume? So for that offset is required. All that will be very easy for you to understand if you have worked with Kafka. Otherwise, you can just read it and watch some videos and stuff. Okay, now once a message is published to the designated partition, Kafka ensures to a robust replication mechanism. Yes, a leader follower model for replication, leader replica. So each partition has a designated. Okay, so we can have replicas, right? Because if data is going to one partition, that becomes one single point of failure. In system design, whenever you have a single point of failure, you need to address it by introducing replications. So we can introduce replication, which means here we have 9 partitions. Let's say we have a replication factor of 3. That would mean that any data to any partition will be replicated to 3 partitions, which means across 3 brokers, we have now total 27 partitions, which will make it fault tolerant, obviously. So now what happens is producer will write to the leader and consumer will read from the leader. Okay. The replicas Now the replication strategy can be different replication strategy. We can have in-sync replicas, which will assume the role of leader if the replicas if the sorry if the leader fails. Okay, so that's what it is talking about here. Leader replica assignment. Each partition has a designated leader replica. Okay, so every partition will have basically a partition has 3 replicas. So one of them is leader, 2 of them are the followers, right? So leader will handle all the read and write requests. So read from consumer and write from partition. And the assignment and all is managed by the controller. So this controller broker will handle all of this metadata stuff. And then we have some obviously from three. So if you have three replicas, one is leader, and two are followers, right? So two are followers, and they will reside on different brokers. Obviously, if they reside on the same broker, then it makes the system less fault tolerant. So they don't directly handle requests, passively replicate the data, which is fine. Synchronization and consistency. Followers continuously sync with the leader. So yeah, they can continuously sync so that they also have a set of latest set of messages, obviously, because they should be consistent, right? So this synchronization is important. Leader, if the leader fails, the follower has to get that role and be promoted to the leader, right? Controller's role in application. Okay, last up, this is also very important line that consumers read messages in a pull-based model. Okay, pull-based. Consumers will pull data from Kafka broker. This is very important. Okay, so which means consumers actively poll the broker for new messages. This is very important. Okay, this is an important point which makes Kafka faster because Kafka has basically, let's say, offloaded this task of pushing data to the consumers. Consumer now has this task to continuously poll and get the data. Okay, excuse me. Yeah, okay. So yes, so as I was saying, that consumers will pull the data, and this makes Kafka faster and more efficient. Okay, okay. So after that, this is some basic commands for Kafka consumer. When to use Kafka? Can be used either as a message queue or a stream. The difference between the two lies in how consumers interact with the data. This seems like a very important point. In a message queue, consumers typically pull messages from the queue. Okay, then they are ready to process them, and stream consumers continuously consume and process messages as they arrive. Okay, okay. Let me just note this down. Actually, I'm also noting stuff down as I'm going through this. See, okay, okay. Consider adding a message queue to your system when you have processing that can be done asynchronously. YouTube is a good example of this. When users upload a video, you can make this camera recognition video available immediately. Kafka topic, all this, okay, we can go through the examples at this time. What you should know about Kafka? The deep dive is rather exhaustive. Don't feel if you are like in the asked, okay. Scalability. Let's start by understanding the constraints of a single Kafka broker. Okay, it's important in your interview to estimate the throughput and number of messages you'll be storing in order to determine whether you need to worry about scaling in the first place. There is no hard limit on the size of a Kafka message as this can be configured via message max slides. Yeah, okay. Yeah, so Kafka message usually is under 1 MB. Okay, to ensure optimal performance. Common anti-pattern to store large blocks of data in Kafka. Kafka is not a database, so not going to store large files. Okay, so this is not a good idea. Okay. On good hardware, single broker can store around 1 TB of data and handle as many as 1 million messages per second. 1 million messages per second. Okay, this is a good estimate. We should keep this in our mind. Okay. Now. Um, Give me 1 minute. Yeah. Okay. So, okay, yes, this is fine. We have a couple of strategies. Horizontal scaling with more brokers. Yeah, simplest way is by adding more brokers to the cluster so that your messages are distributed, and it offers great fault tolerance. Each broker can handle a portion of traffic. Okay, okay. The simplest way to scale Kafka is by adding more focus to the cluster. If you are under partition, you won't be able to take advantage of these new. Okay, partitioning strategy. This should be the main focus of a scaling strategy in an interview, and this is the main decision you make when dealing with Kafka clusters. You need to decide how to partition your data across the brokers. You need to decide how to partition your data across the brokers. This is done by choosing a key for your messages. The partition is determined by hashing the key using a hash function by default. Yeah, basically how to determine which partition to send the message to, that is an important question. So if you choose a bad key, what can happen is that one of the partitions may be overloaded with too much of the traffic. Okay, so it is basically this is a very famous problem called hot partition problem. Good keys are ones that are evenly distributed. Okay, many skin made easy via this, okay, they're usually thinking about scaling topics rather than entire cluster. Because that is you may have a topic that is very high throughput and needs to be a partition across many brokers. All right. How can we handle hot partitions? Interviewers love to ask this question. This is a very important question as well. So let's just prepare. So, okay. So, so how do we handle hot partitions? Consider where Kafka stores. We would start by partitioning by add ID. Okay. So basically, this line actually means that we might suppose if we have three partitions, we can just probably give a hash function like add ID modulo 3, and based on 012, we are uh, routing the message to the zero partition one, like partition zero, partition one, or partition two, okay, something like that. But if there is if suddenly there are too many uh, a burst of traffic for a particular ID, so you'll have a hot partition. That basically means that you will have burst of messages in a partition, and then the load will not be evenly distributed. So how to handle hot partitions, random partitioning with no key? So this is like in 90% of the cases, this is the go-to solution. That we should not give any partitioning key. Rather, we leave this strategy to Kafka. So if we don't provide any partitioning key, and if we give this responsibility to Kafka, Kafka will itself figure out, or Kafka will itself employ or deploy its own partition algorithm to figure out which partition it should send the message to. So that will guarantee event distribution. And obviously, but we lose the ability to guarantee order of messages. Random sorting. We can add a random number of timestamp to the add ID when generating the partition group. This can help in distributing the load more evenly. Okay, use a compound key. Use a combination of ID and another attribute. Okay, back pressure. Depending on your requirements, is just, yeah, back pressure is, I stumbled upon this as a solution to some other issue as well today itself. So seems like it's an important topic, back pressure. So depending on your requirements, one easy solution is to just slow down the producer. Okay, so if you're using a managed Kafka service, they may have built mechanisms to handle this. Okay, so basically, if the lag is too much and there is a burst of traffic and producer is producing too much messages, then we can slow down the producer. Fault tolerance and durability. Okay, okay. So fault tolerance and durability to choose Kafka one reason may have been because of its strong durability guarantees. Yeah, because Kafka will ensure your data is not lost. Okay, data is safe. Okay, Kafka ensures data durability through its replication mechanism. Each partition is replicated across multiple brokers with one broker acting as a leader and others as followers. Hmm, okay. These are basic stuff. You can just go through it. What happens when consumer goes down? So if consumer goes down, the data keeps on adding up, and when the consumer will come up again, it will pick the latest offset after which it was able to read the messages, and from the next offset, it will continue this. It will continue the consuming of messages. Yeah, and rebalancing when part of a consumer group. Agar if some consumer goes down, then the partitions are redistributed and among the remaining consumers so that all partitions are still being processed. Okay. Handling retries, producer retries, you may fail to get a message to Kafka in the first place, errors can occur. So Kafka producers support automatic retries. Now all these are metadata which we can feed in the producer whenever we are, configuring our producer. Yes, okay. Consumer retries. Consumer also may fail to process a message. So Kafka does not support retries for consumers out of the box. Okay, we can move to a message. Okay, 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 okay. Okay, so it basically it is saying that we don't have any out-of-the-box solution provided by Kafka if in case a consumer fails to process the message. So what we can do is we can have a custom topic for storing for storing the failed messages and a separate consumer which will then try to process that. So we can retry as many times because then that algorithm will be defined by us or written by us. This way we can retry messages as many times as we want without affecting the main consumer. So given is required to we can move it to a dead letter queue. This dead letter queue is also a very important term in system design that is used in multiple places. So dead letter queues are just a place to store failed messages so that we can investigate them later. Investigate them and to figure out system issues and bugs and stuff. Okay, performance optimizations. Performance optimizations, especially when using Kafka, we need to be mindful of performance so that you can process messages as quickly as possible. The first thing you can do is batch messages in the producer before sending them to Kafka. Yes, this is again just a simple configuration. I mean, you don't have to go into these details. It's really not required. These are simple configurations. Nothing else. Just whenever you are configuring your producer, you can add these small stuff. There are some compression algorithms as well. Let it be. Retention policies, summary. Yeah, okay. So this I've already done. Okay, so let's also go through this. Here I have written, basically I was going through the, I've gone through Kafka, like multiple resources, so I've noted on every step here. So it's persistent, distributed, replicated, highly scalable, elastic, fault tolerant, pubs up, commit log. So all of these we have just read through and can support even 1 lakh messages per second. Here it was mentioned 1 million messages per second. 1 million messages per second. Even that much is supported. So 1 lakh is obviously supported. So let me just make it 1 million messages per second. Okay. So these are some components. Let me just remove this. Okay. And DB throughput very less. Data can be calculated after picking from Kafka. Okay. So these small points which I have noted down, I'll just remove the points which are no longer required. So Kafka topics are logical partitions. Topics are logical grouping of messages. Partitions are physical grouping of messages. Let it be. Yeah. So publish and subscribe to publish and subscribe to a stream of events. Store events for as long as you want and process as they arrive or later. Producer will send data to a topic, consumer subscribe to a topic. Why not an alternative to DB? Because its throughput is very high, but storage space is low. DB has vast amount of storage space, okay? But uh, Kafka storage is less, okay? And we cannot vary the data. Throughput is high, which means we can store as many data, okay? Okay. This, let's just note it down here. Okay, if only one consumer present, that consumer will consume all the partitions, correct? But if we have multiple consumers, it's not all the consumers will not consume all the messages. Okay, if there are two consumers, 50% messages will be consumed by one consumer, the other 50% of the messages will be consumed by another consumer. This is very important. Okay, auto balancing will be done. And by two partitions, data goes to one server. Basically, if you have 10 partitions, okay, and two consumers, so five partitions data will go to one server, and the remaining five partition data to another server. Okay, so whatever this thing will be done, that will be on a partition level. Okay, if we have one partition, the data will go to one consumer. Simple. If we have one partition and two consumers, consumer number is greater, consumer number is two, and partition count is only one. So the extra consumers, here the extra is 1, 2 minus 1, 1. So it won't get any message from Kafka. It won't get any message from Kafka. Okay, this is important. Here, one consumer can consume multiple partitions. This is also important. One consumer can get data from multiple partitions, but one partition can be consumed by only one consumer. This is a very easy line, but to understand it, you should have understood this part. Okay, consumer groups. Yeah, so there exists a concept of consumer groups. Okay, consumer groups are basically any consumer exists in a consumer group. Within a consumer group, balancing happens. If we have four partitions and five consumers in one consumer group, so according to this logic, one consumer will be identical. But if we have another consumer group, that consumer group will also consume all the data. Okay, so consumer group as a whole is a different entity. Okay, so consumer group one has five consumers, so one is idle. But if consumer group two comes up with suppose one consumer, then it will consume data from all four partitions. If it has four consumers, then it will consume data, like all the consumers will consume from all four partitions. Basically, one consumer will consume from one partition, and like so. Balancing happens on a peak level. This is also an important concept of consumer groups. Okay. Uh, okay, these are Kafka components. These are Kafka components. Okay. So yeah, one message topic, different office, different producer, broker will receive message from producer, assign the offset and commit them to the disk. That's what a broker will do. Consumer uses offset to track the last message consumed. Consumer uses offset to track the last message consumed. Consumer group. One member of group consumes only one partition. One member of group consumes only one partition. Yeah, this is very important. So this line will clear that consumer group thing. Okay, Kafka varieties order from reserving in a single partition only. Folder is not important. Send null keys. Default partition will take care of load balancing messages across all available partitions. Messages with same key are sent to same partition. The leader of a partition consumes messages in the same order. Leader of a partition consumes messages in the same order. A topic can be scaled across multiple. Okay, this all we have gone through and understood. This is Kafka. Why Kafka uses file system? High throughput system. What is the rationale of using file system to store messages? Creates cache optimization. It has skipping one thread. Okay. Okay. I don't think it's required for our interviews anyways. How Kafka maintains the data for so long? Log compaction. Okay. Use in memory data. Listens. Customer use customer benefits. 500 logs. Okay. We don't need these so many details. Okay. Let's just go to this part. Q has 127 consumer, Kafka 127 many consumer, Kafka. This is about event sourcing. It's not needed here. It reads in sync replicas. Yeah, basically you can read about it in sync replicas, out of sync replicas, preferred leader, compaction and stuff. Okay, and these are some of the URLs I went through, basically some of the resources I went through. So yeah, okay. I think this much is enough for Kafka. Now what we can do is we can go through some of the questions. Okay. How does Kafka ensure ordering of messages? Can it be guaranteed globally? So ordering is guaranteed within a partition. This we have to keep in mind. Ordering is guaranteed per partition. Since messages are conducted sequentially, it does not guarantee global ordering to achieve ordering for a key, especially messages with the same key. A single partition which kills parallelism and throughput. Okay. What happens if a Kafka consumer crashes after processing a message but before committing the offset? If it has not committed the offset, it will reread the message ID, reprocess the message. Okay. It will reprocess the message since it was not committed. Please avoid duplication to get exactly one semantics which Kafka transactions. I don't I don't think I need these many details, but this this much I should be aware that it will reprocess after restart since offset wasn't committed, which is quite obvious. Okay, quite obvious. Now, how does Kafka handle leader failure? So if leader fails, whichever replica is in sync is made the leader, and that thing is done by the controller or zookeeper. It would be made the leader. Okay, elects a new leader from in sync replicas. Correct, correct. In sync replicas. But whichever replica is in sync. So I'm also noting down these questions, these question answers on my Notion, so that I can go through them. So if ISR exists, if ISR exists, new leader is chosen. If it is not, select a non-ISR replica. So this particular is. Okay, okay, okay. What is the difference between log compaction and log retention? Okay, log compaction, I thought it was a high level stuff. Log compaction. Log compaction ensures that Kafka will always retain at least the last known value for each message key within the log of the data. Log retention deletes messages older than retention or larger than itna. That is fine. It retains latest value per key. Deletes old versions. Okay, 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 okay. 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 This probably we should be knowing log compaction. Then how does Kafka ensure high throughput? Sequential describes via commit log, page cache, yeah, batching of messages, compression, partition parallelism to scale for throughput. So all of this we have already studied. This is just a revision for us. Hmm. Sequential describes via commit log, page cache, then we have batching, then we have partition parallelism to scale throughput. Okay. How does consumer group rebalancing work? Why is it expensive? Consumer group, I don't think I need this much detail. What's the difference between a Kafka's exactly implementation and it's not required? If the number of partitions in a topic is increased, so hashing the key changes and key map to new partition, taking key disordering, rebalancing it. If key ordering matters, yes, okay. What is the role of instant replicas? Fully caught up with the leader, if replica present, remove from Meza, only as an emphasize for leader election. Correct. What are some trade-offs in setting partition count and replication factor? More partitions obviously have parallelism, put more open file handles, memory, but okay. Okay, this is a disadvantage. And replication factor, higher replication factor, so better fault tolerance obviously, but more storage, network overhead, network overhead. Okay. What happens if the producer sends messages faster? Then back pressure, back pressure, back pressure. Back pressure via distributor, brokers overwhelm, messages pile up in producer buffer is full, understood as configured, correct. Okay. Use of playing parity state consistency when consuming from Kafka. Use change log updates, okay, how does Kafka differ from traditional message queue? Distributed commit log, persistent, high throughput, RabbitMQ in memory, push based, this is pull based, full model, yeah, partition for scaling, okay, yeah, okay. I think this much is enough. We have covered Kafka in enough details, I believe. Hmm. Okay, 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 okay. Should we, this is done. What is this? Common patterns. The ability to identify common patterns, pushing real-time updates. Okay, okay, these are some common patterns which we can go through. Okay, yeah, right now my agenda is to, I've gone through this chapter completely. and noted down some important stuff, whatever I felt was important. And so this chapter is done. Like I might revise it sometime later, maybe tomorrow or day after tomorrow. Let's go through this chapter. Back of the envelope estimation. Back of the envelope estimation. So basically, these are some capacity estimations, some numbers we should be aware of. They don't really matter, but they might matter. So it's good to be prepared. This table was present in Hello Interview capacity estimation page as well, so that I've gone through. Latency numbers every programmer should know. L1 cache difference, nanoseconds, 1 MB sequentially, okay, microsecond, disk heat in milliseconds. Okay. 1 MB sequentially from the network, 10 milliseconds. 1 MB sequentially from disk, 30 milliseconds. Okay, milliseconds. Okay. Build a tool to visualize it. We also take the time factor into consideration. Memory is fast, but disk is slow. Obviously, RAM is fast, disk is slow. What disk is compress data before sending it over the internet. So obviously, compressed data is faster. That's good. Compressed data. Data centers are usually in different regions and takes time to send data into data. Availability numbers. High availability is the ability of the system to be continuously operational for a day. Long period of time. It's not really needed. Let's say. Let's just get to move ahead. Twitter queries for second and storage requirements. So assumption is 300 million monthly active users. 300 million monthly active say, okay, so from monthly active to calculate daily active, it has taken 50%. Okay, so this we should be aware of. We can go for 50% assumption when if we have been given monthly active to daily active. Okay, so 150 million tweet query tweets per second is 150 million and 2 tweets per day. 2 tweets like per day. Okay, so per second calculation it has done. Peak QPS 7000. Okay, we only estimate media storage. So a tweet might have particular tweet ID 64 byte text 140 byte media 1 MB. So 150 million tweets into 2. 150 million users into 2. These many tweets and 10% is what? 10% of tweets contain media. Okay. 10% 1 MB. Because basically in comparison to 1 MB, this 204 bytes, we can just ignore this much calculation. That is right. So for media storage, this is going for 1 MB, 30 TB per day. Okay, 30 TB per day. Okay, tips is all about the process. Solving the problem is more important. Yeah, I mean this is not really very important for the interviews. It's good to know. It's a good to know thing. Okay, or maybe nice to know something like that. There's no need to be spending. Yeah, we can just round off this stuff. Okay, QPS, PQPS, storage, cache, and practices calculations. Okay, so chapter 2 is done. It's quite easy. Data set number, chapter 2. Okay, let's go to chapter 3, which is the framework. I'm not sure if the framework is same as the delivery framework given here. Okay, so framework for system design interviews, we have the standard of awards, coveted on-site interview at your dream company. The hiring coordinator sends you a schedule. Tools, four step. Understand the problem and establish design scope. Propose high-level design. Okay, so basically I've gone through the delivery framework in Hello Interview and I'll follow that only. So for their delivery framework, we have some limited number of steps. One is requirements gathering, which includes both functional and non-functional requirements. Then we have to figure out identify the core entities of the system, and then if some API design is required, and after that we can go to HLD, and after that deep dive is required. Or no, deep dive I probably feel is not required because mostly when we will be working on these steps, the interviewers will keep on asking questions. He will continue asking questions, so you won't really have this much time. Sorry. So yeah. Anyways, that is why I'm not going through this chapter because I have a particular one framework in my mind, so I'll just go with that framework. It's not required to go through the framework, delivery framework. Questions. There is right, neither right answer nor the best answer. Communicate multiple approaches. Once you agree, go into details, bounce ideas of the work, and once prepare the team. Don't hesitate to ask. Communicate, don't keep the silence. Yeah, okay. Basic stuff, basic stuff. Yeah. Chapter 4, design a great mentor. This is a very important problem, and I'm wanting to work on that problem. Okay, okay. Okay. Actually, so right now I have two major questions which I will work on. One is rate limiter, another is cache. So distributed rate limiter, distributed cache, both LLD, both from LLD perspective and HLD perspective. Also, they can be asked in TSA as well. So these two are very important questions. So that is my agenda for the next day. I mean, I'll go to rate limiter right now, but I'll be ending the stream and I'll work on it. And let's say if I finish stream tomorrow, we will meet and then we'll work on the public. Basically, we can revise this rate limiter stuff. Okay. So for now, yeah, I think this is it. Should we go through something else as well? Let me check. Let me check. So we can actually revise this much part. We can do that revision now, or we can do it tomorrow. So let's do it tomorrow itself because right now I think I should focus on this designing a rate limiter. Okay, I really want to work on that question. I'm actually excited for that question. So yeah, I'll work on that designing a rate limiter. So yeah, that's it. I'll stop the stream. Thank you. Thanks for watching. Thanks for joining. Okay, bye bye.